Okay, so let me begin by introducing algebraic coding theory. Now, we talked about coding theory in terms of cryptography. Cryptography is to make messages secret. That's actually not the most common and most important use of coding theory. Coding theory is used in communication. Whenever you use your cell phone, you're using coding theory. The reason why you use coding theory in cellular communications is when you transmit data, you're transmitting it over a medium, or for phones, you're transmitting over a phone line. Whenever you transmit information over a medium, the message is affected by noise. This noise can corrupt the message. So you want to be able to send the information in such a way that any errors introduced by noise can be corrected. Now, when you're sending messages over phone lines, that's not as much of a problem, but just imagine if you're sending information over the airwaves with all kinds of other signals going on. You can imagine there's a huge amount of noise that's present in the communications channel. So this coding theory is the way that people deal with this. It's an extremely important topic, and millions, if not billions of dollars are invested in coding theory and coding theory innovations in the communications industry. Now, one of the nice things about coding theory is it does rely very much on concepts that we've talked about. For instance, modular arithmetic, cosets, and groups. So we'll get there in a little bit. Let me first talk about coding theory basic terminology. All right, so here he talks about a simple model of a communication system. So let me jump to that figure, which is on the next page. All right, so this is a typical diagram of a communications link. And one thing to notice is that here you have encoder on the inside and decoder on the outside. Here you have transmitter on the inside and you have receiver on the outside. So this part is what the source does, and then this part is what the receiver does. And then here's where the channel is, right here. Okay, so the blocks in the source basically dress up the message, and then the blocks in the receiver undo the dressing up so that you recover the original message. Okay. Another thing to notice here is he has an M-digit message that's turned into an N-digit code word. Now, typically, the number of digits in the code word is going to be bigger than the number of digits in the message. The reason is you want to build in some redundancy. Some of the information that you're going to send is to help you correct errors that may be introduced when the noise affects the message. Okay, so the receiver, what the receiver receives is some kind of signal, some kind of electromagnetic oscillation usually, and from that signal it recovers the N-digit received word. Now, I'm not going to really talk about that process. I spent several years actually working on that portion of the communications link. What we're going to talk more about is the encoding and the decoding. Now, the decoding takes the N-digit code word, this is the code word, and it turns it into the original message. Okay, so here again, here you're jacking up the message, adding more information so to counteract the noise. Here you're stripping off that extra information to recover the original message. But those extra bits, those extra digits, are not wasted. Those are used to confirm the validity of the message and to even correct errors that might be introduced by the noise. Another important word here in this section is binary. Now, I mentioned that we're going to use modular arithmetic. In coding theory, the modulus is usually 2. We're going to be doing a lot with Z2. Now, Z2 is the set 0, 1. That's actually the basic unit of information when information is transmitted electronically. You've probably heard of a bit, A bit is 1 unit of information. A bit can either be 0 or 1. Okay, so that's what's actually sent over the airwaves are bits, sequences of bits. Now bits are also grouped into bytes. A byte is a sequence of 8 bits. And there's even more divisions, but byte is what's kind of the basic unit. You may have seen your hard drive is rated in gigabytes or GB. Okay, you have megabyte storage. You have megabytes per second on a channel, on a communications channel. So a byte is 8 bits and measures the amount of information. Okay, we have an example here of a possible coding scheme. So remember, we're trying to code things in order to counteract the effects of noise that might introduce errors. Okay, so suppose let's take this sequence of bits. Either each one of these x's is equal to 0 or 1, so I can say xi is either equal to 0 or 1. So I shouldn't say equal here, it says xi is an element of 0, 1. All right, so this is the message that I want to send. Okay, n bits. All right. Now one way to try to counteract against errors is just simply say it 3 times. This is the child method, right? You say, clean your room, clean your room, clean your room. So if the child doesn't hear it the first time, they may hear it the second time or the third time. Okay, so with messages like this, you can actually apply it bit by bit. He gives an example here. Suppose the original message is 0110, and suppose, and here's what it will be transmitted. You transmitted that message 3 times. Now suppose the noise causes it to have a transmission error in the 5th digit. That means that this 5th digit here isn't received as 0. It's actually received as a 1. So what the receiver sees is 0110, 1110, 0110. So how do we decode this received code word? Well, we do majority rule. To see the first bit in the message, you look at the first bit here, which is 0, first bit here, which is 1, first bit here, which is 0. 2 of them are 0, 1 of them is 1. So most likely, it's the 1 that's wrong. And so 0 wins, and 0 is treated as the first bit in the decoded message. So then you go on to the second bit. Suppose this second bit was wrong. Suppose that second bit came as a 0. Remember, the bits can only be decoded as 1 or 0. The machine is that smart to know that it has to be either a 1 or a 0. So in the second bit, we'd have 1, 1, and 0. Majority rule says it's decoded as a 1. So you go through the 4 bits like this, and you do majority rule on each one of these bits, and you get a decoded message. Now notice that if there were 2 bits wrong in the same place, then it would be decoded wrongly. All right. Now there's always some possibility for error in decoding. If there's a lot of noise, then maybe all the digits might be wrong, and you just get random garbage. So the more noise, the more likely it is to have that there's something wrong with the message. Okay, so you might think, well, this solves the problem. If we want to transmit a message without error, all we have to do is send it 3, 4, 5, 6, 7, 8 times. And if we send it 8 times, then most likely, and we do majority rule on 8 bits, then it would need to have 4 or more errors to be decoded wrongly. Well, that's fine, but the problem is it's expensive to transmit digits. There's something called bandwidth. Bandwidth is very, very expensive, hugely expensive, especially since bandwidth is limited. There's only a certain amount of bits that can be sent over the airways, and different companies pay, again, millions and even billions of dollars to get bandwidth. So to be able to send the same message with fewer bits is economically, it's the holy grail of communications. And even a decrease in 1% of the amount of bits needed to send a message could be worth millions and perhaps billions of dollars. So that's why this field is such a important commercially important field. Okay, well, let me talk about parity check. This is very common in your computer. So here, this introduces the ASCII code that you may have heard about. You know, every key on your typewriter, every letter, every symbol that you type into the computer has a code. There are 128 basic symbols, so there's 128 ASCII characters. 128 is 2 to the 7th. All right. This could be represented by 7 digits or 7 bits, 7 binary digits. No, but it turns out ASCII code has 8 digits. For instance, here A is 65. In binary, this 10 means binary, not base 10. Well, no, I'm sorry. I was wrong about that. This is A is 65 in base 10. If you convert 65 base 10 to base 2, what do you get? Well, just briefly, to convert to base 2, what you have to do is find out the powers of 2 that fit into 65. 65 is equal to, what's the largest power of 2? That's 64. Okay, and then what's the next, after you've taken out the 64, there's only one left. So that's 64 plus 0. 64 is 2 to the 6th. It's useful to remember your powers of 2, and that's plus 2 to the 0. All right, so the bits are numbered here from 0 up to 8. 0, 1, 2, 3, 4, 5, 6, 7, 8. The 0th bit is here, so this 1 corresponds to 2 to the 0. This 1 here corresponds to 2 to the 6th. The 2 to the 6th bit is in the 7th place because the 2 to the 0 bit is in the first place. Now notice there's this 1 bit hanging out in front. That's actually not needed for coding the characters because you can already code them all using 7 bits. So what's the use of this last bit here? This last bit can actually be used for error checking. And the way that's done is as follows. Notice, for instance, this 65. 65, in the code for 65, there's 1, 2, 1s. Okay, there's an even number of 1s here. Okay. In this 66, there's also 1, 2, so this also has an even number of 1s. Here, 67, 1, 1, 1, 1. This has an odd number of 1s. Okay, so what you do is you use the leading digit to indicate whether the original character has an even number or an odd number of 1s in its binary representation. So when you transmit the 65, since 65 has an even number of 1s in its binary representation, you would transmit this bit as a 0. In B, for B, 66, it's the same. For B, C67, you would transmit this 0 as a 1. And that leading 1 indicates that, okay, the character that I'm transmitting has an odd number of 1s in its binary representation. So if you receive even number of 1s in the next 7 bits, you know that there's been an error. Unfortunately, you don't know where it is, but you do know there's been an error. So this scheme, whereas you use 1 bit to check the number of 1s in the remaining bits, is called a parity check, and this leading bit is called a parity check bit. Okay, this paragraph outlines the advantages and disadvantages of parity check. Parity check is easy to implement, but you cannot detect multiple errors. Suppose you have 2 errors, then that won't be detected. You think about that and see why that's true. Second, you cannot correct errors. So this scheme is useful, but the usefulness is limited. Okay.